Welcome, everyone. It's really exciting to see so many of you joining us today. I think this is the biggest stream we've had in a while, which is great to see. So I'm Ryan, and I'm going to be talking to you about black holes, gravity, and dark matter, and how this all works to hold our universe together. But before we get into talking about these really interesting and strange things, I'll just say a bit about myself. So I work at the Space Telescope Science Institute, and as my job, I hunt for stars that explode very far away from us. And I use telescopes there both in space and on the ground to collect as much information as we can get about these exploding stars to try and understand how we can use them to better understand the universe. But in my spare time, I also make some science videos. And some of those have been on questions that young stars like yourselves have had that we haven't been able to answer during these sessions. So some of my favorites were, what are pulsars? How do galaxies collide? And why do rockets blow up sometimes? So you can find these videos and a bunch more on my YouTube channel if you just search Ryan Ridden. So with that out of the way, let's get into some questions, not for me, but for you. How do we stick to the Earth? So the chat will be opened up and you can show us, or you can talk and say what your suggestions are. But keep in mind that a lot of you are joining us from Australia, which is fantastic. So you're stuck on the Earth on that side of the world. I'm on the other side of the world, and I'm stuck in America on the almost complete opposite side of the world. So I'm seeing a lot of responses in the Zoom chat, which all say gravity. And this is precisely correct. So that is what we're going to be talking about today and how gravity actually works in our universe. So the next question I'm going to ask you is, what is gravity? I'll give you a moment to think about how you want to try and type a quick response for this. A force? Oh, that's a really good answer. Any other ideas for what gravity might be? A force that pulls us towards the Earth's core. Gravity is a force that attracts matter to other matter. Gravity and space-time. Wow, man, all of these are fantastic. Good work, everyone. And now there are way too many comments for me to read, so this is cool. Great to have so many responses. It looks like you're all on the right track, so that's great to see. So we're probably familiar with gravity in the sense of, say, an apple falling off of a tree, and it will drop down and bounce on the ground a bit. But if you're asked to a physicist what gravity is to them, they might give you this funny looking thing. So this is the equation of gravity that tells us how much force an object, or how much gravitational force is acting on an object. But this is tricky physics, so we'll get rid of that equation. We don't need it for now. Instead, let's look at the mechanisms behind what makes gravity work. So the main mechanism, which some of you suggested in the chat already, is gravity works on things that have mass. So everything in our universe has mass. Myself, you, everything around us that we can touch and interact with has a mass. And everything that has a mass has a gravitational pull. And these gravitational pulls will be tugging on everything. So just sitting in your room, you're being tugged on by the walls, the ceiling, the air molecules. But these tugs from gravity are very small. You need a lot of mass before the tugs are strong enough for you to actually notice. And something that is strong enough for us to notice is the Earth. And the Earth has a pretty spectacularly large mass. This is the mass in kilograms of the Earth. Now, I'm not going to try and name this number here because there are far too many zeros for me to count. And in fact, there's 24 zeros there. And this is a small number as far as gravity is concerned. So we're going to use something called scientific notation to compress all of the zeros into a number that's times 10 raised to the power of something. So in this case, the Earth's mass turns into 6 times 10 to the power of 24 kgs. So that just means that there are 24 zeros behind that 6. So it's an enormous number. And what else we have that has gravity is the moon. And the moon has a mass of 7 times 10 to the power of 22 kilograms. So it's 100 times less massive than the Earth. And as many of you may recognize, the moon actually orbits around the Earth. So we have a case where the object with the largest amount of mass makes something with a smaller amount of mass go around it. So that's one example. So maybe we should look for another example. And let's look at the biggest thing in our solar system, the sun. And the sun has an awful lot of mass. It has 6 times 10 to the power of 30 kilograms. So it has 30 zeros behind that 2, which is an absolutely enormous number. And if we put the Earth up for comparison, let's shrink the Earth so it's about the same size correctly. So the Earth is 6 times 10 to the power of 24 kilograms. So the sun is about 1 million times heavier than the Earth. The sun is so heavy, in fact, that it contains about 99.9% of all the mass in the solar system. And that's why the Earth and all the other planets, asteroids, and comets within our solar system orbit around the sun, because the sun is just so incredibly massive. So it seems to be a pretty reasonable thing to say that objects will orbit something else that has the biggest mass, or gravity will tend to pull you to the object that has the largest mass close by. So the next question I have for you all, if we open up the chat again, is, oops, oh no, I'm skipping ahead of myself, sorry. So here's the physics equation up again. You can notice that these M's are highlighted now. So maybe as we go through this talk, we'll decode some of what this physics equation means. But suffice to say, on the top here, we have M being multiplied by another M, and those probably stand for the masses of the objects the gravitational force is acting on, which we just talked about. But now that I've caught up with myself, does gravity weaken? So let's open up the chat again and see what you think. If we travel away from the Earth, will the Earth's gravitational pull be less on us? So we've got some people saying yes, it will. Yep, good. All right, I see a very long stream of yeses. Some people said no, which is good because that means that I'll be able to, you'll be able to learn something during this talk. Brilliant. So gravity, does it change with distance? So a good example of this is the Earth and Moon. In the 1960s, something interesting happened between the Earth and Moon. And that was the Apollo mission launched from the Earth and landed on the surface of the Moon. Now, if the Earth's much bigger and has a stronger gravitational pull than the Moon, then the Apollo mission shouldn't really have been able to land on the Moon if the gravitational pull didn't get any weaker. But instead, this did happen. The Apollo module, or the Eagle module, did land on the Moon, and we had astronauts skip around on the lunar surface, dropping things as they went and falling over as well. So you can see that they're sufficiently far away from the Earth that the Earth's gravity isn't as strong as what the Moon's gravity is on them now. And if you remember before, the Moon had about 100 times less mass than the Earth. So the thing that really plays its role here is the distance between the two objects. So they're much further away from the Earth, so the gravitational pull of the Earth is weaker on them. They're very close to the Moon, so the gravitational pull of the Moon is very strong for them. And what's this? It's our physics equation creeping up on the side again. So now we have this other thing that's been highlighted, this r to the power of 2. Whoops, where did it go? So what this is probably saying is that the strength of gravity depends on how far away you are from an object. So the further away you are from something, the weaker the gravitational force is going to be. So that seems to make sense for now. So let's get rid of that. And the next question is going to be, how strong is gravity? Now, I'm going to make a bet that every single one of you are stronger than an entire planet of mass, of gravity. And the reason I'm going to say that is because we can pick things up. Like I can pick up my phone right now, and just like that, I'm stronger, have applied more force to this phone than an entire planet's worth of material. But the trick is that the force of gravity is always attractive and always pulling. So as soon as I stop applying a force to the phone, gravity wins and the phone drops down to the earth. So gravity is always working, but it is kind of a weak force if we're stronger than gravity with our arms and legs. But the thing is that if you have enough energy and enough force to get away from the Earth entirely, you've won. You've beaten gravity and you're away and don't have to worry about it anymore. But if you stop applying a force before you escape the Earth's gravitational pull, disaster strikes. And in this case, we have a tragedy with our massive Apollo rocket blowing up on the Earth's surface many times over. So this is the case of gravity. It's incredibly weak. And now if we go back to our friendly equation that's been coming up all the time, we now find that the G is highlighted. And this G is a very special number. It's called the gravitational constant. And it's one of the reasons why gravity is so weak. It's been measured, and it's a property of our universe, and it's been measured to about this number here, 0.00000000007 meters cubed per kilogram per second squared. So this could be written as 7 times 10 to the minus 11. So it's an incredibly small number. So the reason gravity is so weak is twofold. One, this G number is an incredibly small number, which turns out to be a good thing. And the distance between two objects, especially in space, is enormous. So both of these numbers, dividing by a very big number and multiplying by a very small number, gives us a very small force. So this is why gravity is such a weak force, because of these numbers and properties that it interacts with. So if gravity is so weak, the question becomes, how does gravity shape the universe? Well, we have 4 fundamental forces in our universe. We have the strong nuclear force, which acts on a subatomic level in between the protons and neutrons with things called quarks. And that's about 10 to the power of 38 times stronger than gravity. So enormously stronger than gravity. We have the weak nuclear force, which again only acts on very short distances within about a proton in distance. So very, very small things. And that's 10 to the power of 32 times stronger than gravity. It's called weak, but it is incredibly strong compared to gravity. And then we have the electromagnetic force, which is, we're familiar with electricity. We have positive and negative charges, and that's 10 to the power of 36 times stronger than gravity. So again, completely dwarfs the strength of gravity. Then we have gravity, the strength of gravity. So why do these other forces, which are incredibly strong compared to gravity, not matter as far as the universe is concerned on the very large scales? Well, the strong nuclear force is so good at what it does, it balances itself out almost entirely. So outside of a proton or neutron, there's effectively no more strong force. The weak nuclear force is called weak because it has a very short range that it acts over. It can't influence anything past, say, the diameter of a proton, the size of a proton. So that certainly can't change the way an entire universe looks. So the weak nuclear force shrinks away. The electromagnetic force is like the strong force. It has ways to cancel itself out. In our universe, it seems we have pretty much the exact equal number of negative charges to positive charges. So if you have positive and negative charge, they effectively cancel out. So again, the electromagnetic force is cancelled. It just doesn't really matter too much. So what we're left with is gravity, the weakest force in the universe, the force that only pulls things towards other objects, is the thing that controls how the universe evolves in its structure over time. So now that we've got the physics out of the way, let's start looking at how gravity works on shaping the universe. So to do that, let's look at the solar system. So in this video here, we have a simulation of our solar system. The sun is sitting right at the center here. Around it are the planets, the inner planets, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, and Saturn. And one thing you might notice is that the planets and objects closer to the sun move around the sun much faster than objects further away from the sun. And this generally makes sense. There's less gravitational force acting upon them, and they've got bigger distances to travel. So it all does seem to make a lot of sense. So the further away you go from an object, the less influence it has on you. So this makes sense. But gravity doesn't just work on the sizes of solar systems, it works on sizes of galaxies. And galaxies are collections of billions of stars and tremendous amounts of gas and dust. And they can move around the universe and tug on each other. And here we have a really cool simulation of two galaxies colliding. So this is perhaps, if you were able to live 5 billion years into the future, what you might see happen between the Andromeda galaxy and our Milky Way. Gravity pulls these two enormous galaxies together. These stars start feeling the gravitational pull of the other galaxy, and they get completely bent out of shape and into these weird and wonderful new objects. So they're not what we call lovely spiral galaxies anymore. This is what we'd call an irregular galaxy. So gravity is busy working away, tugging on all of these objects, trying to pull them back into a reasonable order, orbiting around the center of this newly forming galaxy. But some of the stuff will escape, like these big arms over here. They might be running away from this merging galaxy, never to return. So although gravity does play a big role, it is still pretty weak. You can escape it if you work a little bit. But if we were to look at a single galaxy, we'd find something quite bizarre. So in this video here, we have an animation of a galaxy rotating. So at the center of the galaxy, it's moving very quickly, as we would expect. It's close to the center of mass of the galaxy, where the gravitational pull should be the strongest. But as you move away from the center of the galaxy, it kind of looks like the stars are moving more or less at the same pace as each other. Now this is an interesting puzzle that is a massive problem, or not necessarily problem, but an outstanding issue in astronomy. It's that galaxies rotate too fast for how much gravity we can see with our eyes or with our instruments. So with this and a whole bunch of other evidence, astronomers have come to the conclusion, which might seem a little strange, that there's probably an awful lot of mass, material out in the universe that's invisible to us, but interacts with the universe through gravity. And all of the galaxies are embedded inside of these big things called dark matter halos. So you may have heard of dark matter. It's this mysterious thing that we haven't directly detected yet, but we have lots of circumstantial evidence to suggest that it actually exists. And if you do some simulations with dark matter, you get something like this. This is an eagle simulation of the universe evolving through time with dark matter. So you can see dark matter is these great big red filaments, these kind of a web-like pattern. So as time goes on, gravity tugs at all of the matter in the universe and pulls it into shape. It makes these big long strings, and it makes these tight areas where there's lots of material, where galaxies are forming and firing material back off into the universe. And all of this happened because of gravity, pretty much. All of the other fundamental forces, as I mentioned before, are all tied together in their own problems. But gravity, even though it's a weak force, can act on a universe worth of material, and given 13.4 billion years, it can guide all of that material into all of these enormous structures that we actually can observe in the universe. So although this might be a simulation, we've conducted observations of the universe that have shown us that this simulation is pretty accurate. So this is a pretty interesting map. And this map tells us where galaxies are positioned in the universe. So it's just the distance away from us. If they measure a galaxy, they'll put it down. And this is just the angle on a sky, so like a piece of a circle. And you can see in this observational data, so this isn't a theoretical model, all of these strings and clumps and all of these walls of material, just like we saw in the simulation. So we know that gravity and dark matter have shaped the universe into this really kind of three-dimensional spiderweb, which is a really cool thing to have. So gravity pulls everything together and sticks everything together in this enormous web. But a good question to ask ourselves now that we've convinced ourselves that gravity can shape a universe is, can there be too much gravity? So let's open up the chat again. What do people think? Can there be too much gravity in the universe? Yes, no, yes. This is a pretty subjective question. So yes, no, sort of, yes. Yeah, I agree, definitely, all right. Strong opinions here. Maybe, yes or no. Yeah, I agree with that one. So it depends on what you mean by too much gravity. So let's look into this a little bit. So let's go back to our friendly physics equation. Now that we know what it all means, here, the force of gravity, G, the gravitational constant, that very small number, M and M, the masses of the objects involved in gravity, and R, the distance between objects. So say we want to try and make an object have too much gravitational pull, and we can't change its mass. Well, we can't change G because that's fundamental to our universe, the gravitational constant. If we were to change that, it would mess up the entire universe. But we can change the radius. We can squish objects down. So let's, for example, take our sun. Our sun is about 1.4 million kilometers in diameter. So what will happen if we just squish it? So let's just do that. So squish the sun right down. It disappeared. It disappeared at around about 6 kilometers in size. So what do you think happened to the sun? So what does everyone think? Where did the sun go? What happened to it? Died, yeah. In a sense, it died. It imploded, yeah. Changed into a black hole, died, black hole, gone. Yep, so the smaller it got, the stronger the gravitational pull became. And there's a point where you might call this too much gravity, that if you compact something so much, the gravitational pull actually becomes incredibly strong, stronger than, say, the electrostatic or electromagnetic forces that might push against gravity normally. And it can pull it down until it disappears entirely. So it would turn into a black hole. And 6 kilometers is the diameter at which our sun would turn into a black hole. It's what we call the Schwarzschild radius. So it's the radius or size at which if you compress something too much, it'll just disappear and become a black hole. But the question is, what is a black hole? Are they actually real? Well, black holes are real, and we have definitive evidence for them now, which is really exciting. If you were to ask this question, say, maybe even just 5 years ago, we would say, well, we have a lot of good evidence to say black holes are real, but we don't have definitive evidence. So what I'm showing you here is probably something that many of you have seen. It's an image from the Event Horizon Telescope of a nearby supermassive black hole in a galaxy close by to us. At the center would be the black hole, and around it is the accretion disk, a disk of material slowly falling into the black hole. Now, if we were to simulate what this would look like in higher resolutions, so not using current limitations with instruments, we would see that the black hole would look something like this. And it looks beautiful, but also quite strange. There's a disk of material going around in front, and it also goes around behind. But before, we saw the disk go above and below it, but from this angle, it looks like this just goes around. So why does the disk get bent up and under like that? Well, it's to do with gravity. So all of this is material orbiting around the black hole, and its light is actually getting messed up by how strong the black hole's gravitational pull is. So to have a better idea of how black holes mess things up, let's watch this video here. So this is just a random galaxy field, and then we'll simulate a black hole passing through. So you can see these galaxies getting all distorted and moved around as the black hole passes through. So this is something we call gravitational lensing. So things that have an awful lot of gravity will bend and warp space into these really strange looking shapes, and the light will be bent and warped around with that space and create those strange images that we saw. So these are things that black holes do, but what exactly are black holes? That's a very good question. A lot of black holes we've found, at least so far, have big disks of material orbiting around them. These are called accretion disks, and they're slowly funneling down into the black hole. But a lot of the time, there's material also being blasted out of the poles or nearabouts the poles. And that's not material coming from the black hole. It's material that the disk is guiding up away from the black hole and firing off into space. So all of this is because of gravity, because the black hole's gravity is so incredibly strong. But this black hole itself is pretty strange. We don't know much about it. We know they exist, but we don't really know too much beyond that. They're at a point where our understanding of physics starts to break down. They're what we call a singularity. So right in the center of the black hole, you could imagine space being compressed so much that there's an infinite amount of space and an infinitely small point in space. So that kind of sounds a bit dubious and perhaps something we shouldn't trust, but that does seem to be the case. And around it, this black ball is what we call the event horizon. Anything that passes through the event horizon can never come out of the event horizon. And this event horizon is kind of the barrier of where our understanding breaks down as well. And you might ask yourself, well, what if I wanted to go explore a black hole and dive through it and tell everyone what's on the other side? Well, you would be in a lot of trouble if you tried to do that, because the gravitational pull of black holes is so strong. As you're falling towards the black hole, all of the atoms in your body and in your spaceship will be torn apart, torn away from one another, and create a stream of material flowing down onto the black hole. And that process is something we call spaghettification. So a very scientific term, because you get turned into a long piece of spaghetti. And I don't think it would be too pleasant. But if you imagine that you could survive being torn or the extreme gravitational pull, something even stranger will happen. If you're watching someone fall in, they'll fall in and they'll fall in slower and slower as they get closer and closer to the black hole, until eventually it looks like they're not falling in at all anymore. So it seems like they just freeze in space. But if you're the person falling into the black hole, to you it seems like you're falling in at a reasonable pace. But if you look up to the universe around you, you'll see something quite bizarre. Time in the universe will be flying by. You'll see stars exploding in a matter of moments, galaxies merging, billions of years, millions, billions of years will be flying by really quickly. And that's because gravity also messes around with time. So the more gravity there is, the slower time ticks. So if you fall into a black hole, your clock will slow down to the point where it almost effectively stops. So you'd be able to watch the universe play out, the evolution of the universe, as you fall into a black hole. But the question of where black holes lead and what exactly they are is something that we're still yet to answer. And we need lots of clever people in the future to go forth and try and understand these crazy objects and all the other crazy things that gravity does in our universe. So now that hopefully you have an understanding of how gravity operates in our universe and how it interacts with different things and how it can create the beautiful structures we see around us today. So I've rambled on for enough now, so let's have some time for some questions.